Welcome to AI Peer Review. We talk a lot about these incredible, massive AI models, pushing the boundaries of capability, but often that vision kind of hits a wall when you think about where these models actually run. Sure, cloud servers have, well, near infinite power, relatively speaking, but what about your phone? Or like that drone inspecting infrastructure? Or the systems embedded in autonomous cars? Getting truly powerful AI onto devices with limited power, limited memory, limited compute, well, that's a huge challenge.
It really is. It's kind of the frontier of practical AI deployment right now. We've seen models get bigger and better, which is amazing, obviously. But it creates this massive gap, between what's possible in a giant data center and what's actually feasible on an edge device. The trend has to move towards not just bigger or smarter, but dramatically more efficient models. If we want to see AI widely adopted outside the cloud, that is.
And that brings us perfectly to the focus of this deep dive. We're looking at an interesting paper that directly tackles this problem. It presents a model called MiniCPM4, and it's specifically engineered to be a highly capable large language model, but built for these exact inside resource-constrained chips.
Yeah, exactly. So our mission here is really to unpack the brilliant technical innovations described in this paper. The specific tricks and techniques that allow an 8 billion parameter model, which is still pretty hefty, to achieve such remarkable efficiency and performance, making it work effectively even where power and memory are really tight constraints.
Okay, let's unpack this quest for edge efficiency then. As you said, the core problem is wrestling these computationally hungry giants down to size for tiny silicon. I mean, while a 70B model is impressive, it's just not running on your smart doorbell anytime soon.
Not a chance.
So MiniCPM4 is an 8B LLM, which is still substantial, yeah. But the paper details these systematic innovations across 4 core areas to make it edge-friendly. That's the model architecture, the data it was trained on, the training methods, and the systems used for inference.
Right, and what's really striking is how they combine all these elements. The paper makes some pretty bold claims about the results, actually. They report MiniCPM4 achieving comparable performance to models like Qwen 38B, but, and this is the kicker, using dramatically less training data. Only about 22% of what Qwen 38B used. And for handling long text, which is crucial for so many real-world tasks, they show a 7-fold speed improvement on end-side devices.
Wow.
Yeah, that's not just incremental, that's a step change, the kind of efficiency you need for the edge.
7-fold speed improvement. On long context. On an edge device, that's massive. I mean, that fundamentally changes what you can actually do on the device itself. Okay, let's dive into how they pulled this off. Starting with the architecture. The paper introduces something called LLMv2. What's the specific pain point this new architecture aims to solve?
Okay, so the main bottleneck, especially when you're dealing with long sequences and you're on limited hardware, is the standard self-attention mechanism, the one in most transformers. It computes relationships between every single pair of tokens in the sequence, and as the sequence length grows, the computation just explodes quadratically. That's OOL.
Right.
So if your text doubles in length, the attention computation quadruples. For very long documents on a small chip, that just quickly becomes impossible. NFLLMv2 addresses this with what they call trainable sparse attention.
Sparse attention. Okay, so that implies it doesn't look at everything. It's more selective.
Exactly. The core idea is smart selection. Instead of attending to every preceding token individually, NFLMv2 operates on blocks of tokens. Think of it like chunking the document into paragraphs or sections, maybe. It partitions the stored history, the key value cache, into these fixed-size blocks. Then, for each new token the model processes, instead of comparing it to every single previous token, it dynamically selects only the most relevant blocks of historical tokens to pay attention to.
Okay, but how does it know which blocks are relevant without reading them all first? That sounds like it could still be slow itself.
That's where the innovation comes in. They use fine-grained semantic kernels. You can kind of think of these as tiny summary fingerprints for each block, very efficient. So when a query token comes in, it compares its fingerprint to the fingerprints of all the blocks. This selection step, comparing the query to block summaries, well, it still has some relationship to the sequence length, but the computational cost for the actual attention is then limited only to the few selected blocks. The paper points out that, yeah, the block selection stage can still look OL, but the critical part, the attention calculation within those selected blocks, is much, much faster. It effectively scales more like OLL for typical use cases, where your sequence length is much bigger than your block size M. It avoids that huge OL matrix multiplication bottleneck of dense attention.
Got it. So the really computationally expensive step, the attention matrix itself, is drastically shrunk. because it only operates on the relevant parts you've pre-selected using those fingerprints. That's where the speedup goes from.
Precisely. And a key design principle they highlight, which is quite important, is that the query computation remains token level, meaning it processes one token at a time while the key value stuff is block level.
Okay.
This is crucial for the decoding phase, right? When the model is actually generating text token by token. If you block the queries, like some other sparse methods do, you can't actually get acceleration during this real-time generation because you don't have a full block of new queries ready yet. Keeping queries token level allows LLM v2 to accelerate both the initial processing of a long document and the subsequent generation of a response, which is exactly what you need for like an interactive application on your device.
That really makes sense. Okay, so an efficient architecture is step one. But efficiency isn't just about the model's design. It's also heavily dependent on what you feed it, right? Training huge models needs enormous amounts of data, which is incredibly expensive and time-consuming to gather and clean. How does MiniCPM4 handle that data challenge more efficiently?
Yeah, that's the next piece. This is where their ultra-clean strategy comes in for data preparation. The problem isn't just needing a lot of data, it's needing high-quality data, really good stuff. And figuring out if a batch of data is truly high quality by, training a full LLM from scratch on it just to see if performance improves, that's just prohibitively expensive. You can't do that repeatedly.
Right, that would take forever. So what's their shortcut for checking data quality then?
It's quite clever, actually. Instead of starting from scratch, they leverage a model that's nearly trained, almost done. They take candidate data and essentially use it for the very final steps of training on this nearly finished model, just a little bit more training. If the model's performance improves after this quick training burst, they consider that data high quality and keep it. If not, they toss it.
Okay.
This is significantly faster than doing a full training run just for validation. You can see the workflow for this in the paper. It shows how they kind of iterate on this.
That is a smart way to validate without burning tons of compute.
Yeah.
Okay, what about filtering the massive amounts of raw data you start with?
That's another big efficiency gain they talk about. While using an LLM itself to classify data quality can be effective, sure, running a huge LLM over potentially trillions of tokens is incredibly slow and expensive. We're talking thousands of GPU hours.
Yeah, ouch.
The paper notes they found a much faster approach, using a fast text-based classifier. It's a simply non-LLM model. It's drastically faster, runs on standard CPUs in a fraction of the time, while still being very effective for filtering at scale. The comparison in the paper shows this huge reduction in computational cost. It's pretty stark.
Okay, so they efficiently filter the raw data and they efficiently verify the quality of batches. Do they also, generate data?
Yes, they do that too. They also use LLMs to synthesize and restructure data. The goal here is to create data that's really dense with knowledge and logic, often structuring it like a textbook chapter or maybe a forum discussion, something like that, to improve the model's reasoning and knowledge acquisition. And this focus on quality and structure, combined with the efficient verification, contributes to that reported ability to achieve high performance with significantly less total training data compared to other models.
Right, so we have an efficient architecture and a smart, efficient data strategy. That covers the foundation. What about the actual training process itself and then getting the model ready to run on devices?
Training efficiency matters too, of course. Can't forget that. They mention using FP8 mixed precision training, which basically leverages newer hardware capabilities for faster computation and reduced memory usage during the main training phase. Then there's post-training, where they refine the model. They use supervised fine-tuning, or SFT, with a high-quality dataset called UltraChat v2 to kind of polish the model's core conversational abilities. And they also use reinforcement learning, RL, to improve its more complex reasoning skills.
RL. That can be tricky to parallelize efficiently, can't it? Especially when the model generates outputs of different lengths.
Yeah.
That load balancing issue.
Absolutely. That's the classic unbalanced load problem in RL rollout. If some responses are really short and others are very long, some GPUs finish their work early while others are still grinding away. It's inefficient. So to address this, they use a chunk-wise rollout strategy during RL. Instead of generating a full response all at once for each training sample, the policy model generates outputs in fixed-length chunks, say 512 tokens at a time, across all samples simultaneously. This keeps the GPUs busy much more consistently. It significantly improves utilization and overall efficiency during that RL training phase.
Smart. And for hardware with even tighter constraints, they push the envelope further. I saw something about a super low-bit version.
Yes, that's MiniCPM4. This is a ternary version, which is pretty extreme. It means the model's weights are constrained to just 3 possible values: mega to 1, 0, or plus 1.
Wow.
This requires incredibly low memory and computation, ideal for the tiniest devices. They achieve this using quantization-aware training, or QAT. But crucially, they use a two-stage QAT process that starts from the already trained high-precision MiniCPM4.
So they don't train the ternary version from nothing.
Right, that would be far too costly. Starting from the pre-trained model is far more efficient. The paper shows they can get performance close to training low-bit models from scratch, but using only about 40% of the total training tokens just for the QAT stage. This makes creating these ultra-efficient versions much more practical.
That's serious miniaturization. Okay, so beyond the core training, getting it to run fast in real time on a device requires specific inference optimizations too. What techniques did they layer on top of the sparse attention we talked about?
Several key ones, yeah. One is called FR-spec, which stands for frequency-ranked speculative sampling. So speculative decoding is a pretty common technique now. You use a smaller, faster draft model to predict the next few tokens, and then the main, more powerful model quickly verifies them. If the draft was right, you save time. FR-spec optimizes the draft model specifically. It restricts its output predictions to only the most frequent tokens in the vocabulary.
So the draft model only considers like the most common words.
Pretty much, yeah. Think about it. Most text uses a relatively small set of common words very, very frequently. By having the draft model focus only on this high-frequency subset, say, the top 25% of the vocabulary, maybe they drastically reduce the computation needed for the draft model's language modeling head. That's often a bottleneck. The main model still operates on the full vocabulary, of course, so accuracy isn't compromised. But the process of drafting potential next tokens gets much faster. The paper has a figure, I think it's figure 6, that helps visualize this idea of vocabulary space compression.
Clever optimization just for that drafting step. Okay.
Yeah.
What about quantization specifically for inference? Shrinking the model weights.
Right. They improved on the standard GPTQ quantization method. Their version is called Prefix-Aware GPTQ, or PGPTQ. They found something interesting. When quantizing models, the very first few tokens processed in a sequence can cause these extreme outlier values in the model's internal activations, especially in the deeper layers.
Really? Just the first few tokens?
Yeah. And these outliers can really mess up the calculation of how to best shrink the model's weights during quantization, the Hessian calculation specifically. So PGPTQ modifies the math used in GPTQ to basically ignore these initial token outliers when it's figuring out the best way to quantize. This leads to better accuracy after shrinking the model down. Table 4 in the paper shows their enhanced version, SPGPTQ, having less performance drop compared to the original FP16 model, beating other quantization methods.
Addressing that specific bias just from the beginning of a sequence, that's a fascinating level of detail. And finally, once you have this super optimized model, you still need to actually run it on all sorts of different hardware, right? Different chips, different operating systems. It's fragmented out there.
Exactly, and that's the role of Arc-Infer. They're a cross-platform deployment system. The reality of the edge is fragmentation. You might be deploying on an NVIDIA Jetson or an Android phone with a specific AI chip, or maybe an embedded system using a different framework like llama.cpp or TensorRT-LLM.
Right, it's a mess.
It is, and building custom deployment code for every single one of those scenarios is just impractical. So Arc-Infer provides a unified architecture. It has this abstraction layer that sits between the model and the hardware. It kind of normalizes the different APIs and frameworks. This allows developers to deploy MiniCPM4 much more easily across diverse hardware platforms without rewriting everything from scratch for each one. It also handles tricky underlying details, like managing the KV cache efficiently across platforms.
Okay. That is a truly comprehensive set of innovations. I mean, touching every stage from the training data, architecture training, quantization, inference optimizations, all the way to deployment. How does this all translate into actual performance and, real-world capability? What do the numbers say?
Yeah, looking at the performance evaluations, especially the inference speeds shown in the paper's figures, is key. Figure 1 is a good one to look at here. They tested MiniCPM4 on actual N-side GPUs, like the NVIDIA Jetson AGX Orin, and even desktop cards like the RTX 4090 for comparison. What's really compelling is that MiniCPM4 shows consistent and significant speedups compared to other models in its class, like Llama 3.8b, GLM 4.9b, and Qwen 3.8b. And especially as the context length grows, going from 32K up to 128K tokens, that's where the sparse attention really shines.
That long context performance is critical.
Absolutely. And the paper specifically highlights that 7x decoding acceleration over Quinn 38B on the Jetson. This really demonstrates the power of their sparse attention and inference optimizations working together on actual edge hardware. It's not just theoretical.
Okay, so it's demonstrably faster where it counts. But speed is kind of useless if the model isn't actually capable, right? How does an 8B model trained with significantly less data stack up against its peers on standard benchmarks? Does it hold its own?
That's the other crucial part. The paper presents standard evaluation results across a wide range of benchmarks, things like MMLU, GSM-8K, Human Eval, covering reasoning, knowledge, coding, and so on. They compare MiniCPM4 8B to other models, typically ranging from, say, 8B to 14B parameters. And what Table 5 generally shows is that MiniCPM4 8B performs really competitively, and in many cases, it actually performs better than many larger models, despite using way less training data.
Better than larger models. Wow.
Yeah. They also show a smaller 0.5B version performing strongly against typical 1B models. This suggests their focus on high-quality data and efficient architecture, and training isn't just about reducing cost or improving speed. It seems to genuinely contribute to maintaining or maybe even improving the model's capabilities relative to its size and the amount of training data it saw. It's really a testament to the synergy of all these different techniques working together.
That balance is seriously impressive. The paper also goes beyond just benchmarks to show a couple of specific applications they built on MiniCPM4 too, right? To show it's practical.
Yes, exactly. Demonstrating the model's practical utility is important. One is called MiniCPM4 Survey. It's fine-tuned specifically to generate high-quality, trustworthy survey papers on technical topics. It uses a specific plan-retrieve-write pipeline to structure the process, and the paper shows this application performing competitively, even against methods using much larger models like GPT-4o. And importantly, it achieves a strong fact score, meaning the information it presents is factually accurate and well-cited.
Generating reliable survey papers on device. That's a pretty cool application. And the other one mentioned?
The other one is MiniCPM4-MCP. This focuses on tool use. It leverages a standardized framework called the Model Context Protocol, or MCP, for interacting with external tools or APIs. It's basically a structured way for the model to understand how to call functions or use APIs correctly. By training MiniCPM4 specifically to use this protocol, they enable it to interact with tools much more reliably. Table 8 compares its tool use accuracy, things like getting the function name, parameter names, and parameter values right against GPT-4o and Qwen 38D. And MiniCPM4 MCP shows really strong performance here, which they attribute to it learning the specific structure and characteristics of interacting through that MCP environment during its fine-tuning.
So yeah, from a clever selective architecture and highly efficient data handling, through optimized training and these smart runtime techniques, all integrated into a flexible deployment system, MiniCPM4 really presents a compelling case study. It covers all the bases.
It absolutely does. It's an 8B model that was clearly designed from the ground up with the constraints of edge hardware in mind, and it seems to prove that you can achieve competitive performance and significant speedups on devices through this kind of holistic approach to efficiency, looking at the entire LLM lifecycle.
This work really does push the boundary, doesn't it? Bringing sophisticated AI capabilities off the giant data center racks and, well, closer to where the data actually is and where the users are. It makes you wonder.
Yeah, it definitely raises an important question for all of us, I think. As AI models continue on this trajectory, becoming smaller, smarter, and vastly more efficient without completely sacrificing capability, what incredible AI applications that we currently only access through the cloud will suddenly become commonplace. On the devices you carry in your pocket, wear on your wrist, or have embedded all throughout your home in the coming years, what becomes possible then?